Okay, so we've covered measures of association for numerical variables, covariance and correlation. We've covered a measure of association for two binary categorical variables, which we call relative risk. Another technique we covered in descriptive statistics is something called simple linear regression. What is simple linear regression? Well, it's used when you have two numerical variables and you want to describe or predict. Specifically, what you're doing is you're fitting a line to a scatter plot of data. In high school, most likely, or in elementary school, or before college, you probably learned that a line can be expressed as y equals mx plus b, where b is some y-intercept or constant, and m is some slope, defined as the rise over the run. But of course, now that we're certified adults, we express the line in this way. This is using notation for a sample and using notation that is common in statistics and related fields. We say y hat, the predicted values of y, equals some intercept plus some slope times x for a sample. Y hat simply refers to the values of our outcome that lie on that line. X is some predictor or input variable. B subscript 0 is the intercept, otherwise known as a constant, and B1 is the slope associated, related to x. This is how we can visualize simple linear regression using the cricket chirps data. Recall that we have 7 rows of our data set. What we're trying to do is we're trying to fit a model to this data set. We're trying to predict the mean temperature in degrees Fahrenheit for different values of x, where x is the number of cricket chirps per minute that we have observed. So our model, all the points on the line can be described by two numbers. Because it's a straight line, all we need is an intercept and a slope to describe this line, to summarize this line. The intercept is simply the value when x is 0. Or to put another way, it's the expected mean when x is 0. And then the slope is simply the value for every, expected change in the outcome for every 1 unit increase or change in x. So we see for every 1 unit change in x, for every additional chirp that we observe per minute, we expect the temperature to increase by 0.23 degrees Fahrenheit. Where the number of cricket chirps observed is 0, the expected temperature is 37 degrees Fahrenheit, roughly. Now, the thing to keep in mind is that the intercept may not be substantively interpretable. That's because it doesn't really make sense to have no cricket chirps. Right? Maybe we'd expect 1 or 2 cricket chirps at least. So keep that in mind when interpreting the intercept. To put it another way, the intercept may lie very far away from the center part of the data. Here we can see the scatter plot has a certain sort of distribution, but the intercept lies pretty far away. Right? So be careful when you interpret the intercept. It may not be substantively meaningful to set x to 0 and then say this is the mean of the outcome when x is 0. Ask yourself if it really makes sense to set x equal to 0. Regardless, the intercept is necessary because it locates the line through the scatter plot of data. So how do we interpret the intercept and slope? Well, the intercept gives the expected mean of the outcome when x is 0, and the slope is the difference in expected means of the outcome for a 1 unit increase in x. Or for shorthand, we might say for every 1 unit increase in x, we expect the outcome to change by whatever the value of that coefficient is. So for the cricket chirps example, we'd say for every 1 unit increase in x, we expect the cricket chirps to increase by 0.23. That slope, right, a positive slope will indicate an upward line going from the lower left-hand corner to the upper right-hand corner of the scatter plot. A negative slope will indicate a downward line. A slope of 0 or near 0 suggests a horizontal or near horizontal line. Now, one thing to keep in mind about fitting a line to a scatter plot of data, it's different than covariance and correlation. Correlation and covariance, well, it gives us a measure of association between two numerical variables, but it doesn't fit a line to a scatter plot of data. The other thing to keep in mind is that with regression, with simple linear regression, what we're doing is we're fitting a model in which we're predicting the mean of our outcome conditional on different values of x. You might say, well, what's the mean temperature when number of cricket chirps is 10? What's the expected expected temperature when the number of cricket chirps is 50? What's the expected temperature or the expected mean temperature equivalently when the number of cricket chirps is 100? Right? We're modeling the mean conditional on different values of x. Correlation and covariance don't do that. They just give a snapshot of one measure summary of the linear relationship between the two variables. So one way to think about the simple linear regression is that it's modeling the mean conditional on different values of x, and accordingly, it matters what your x and y variable are. Meaning if you switch your x and y variables with simple linear regression, you're going to get different results because it means something different to model the mean of degrees Fahrenheit given different values of cricket chirps versus modeling the mean number of cricket chirps for different values of the temperature. So key point here, correlation covariance, you can switch the x and y variables to get the same numerical summary. With simple linear regression, be careful, ask yourself, what's your y variable, what's your x variable? You shouldn't switch the two. So how do we interpret the output? This is the output using statistical software. We expect the mean temperature to be about 37.8 degrees Fahrenheit with there no chirps. And then of course, for every 1 unit increase in temperature, the expected mean temperature increases by 0.23 roughly degrees Fahrenheit. Another point when we look at simple linear regression has to deal with what we call the errors or residuals. Each of the observations in our data set, each of those data points, each of the rows of our data frame, right, they each have an outcome y, a raw outcome, but they also have a predicted value. That predicted value is the difference between the raw outcome for each observation and the point on the line for that particular observation. That's the error, that's the residual. That is how far off our expected mean from our line is from the actual value of the data. We call these errors. Right? In general, we want a regression line. Right? We want a line fit to the data that makes it so that these errors, collectively, these residuals, are pretty small. They're pretty close. To put it another way, we want these residuals to be not that large. You know, they're all kind of close to the line. You might have a few people or a few observations with pretty large residuals, but on average, you want these residuals to be relatively close. Right? So here you can see that we can talk about a fitted versus residual components of our model. So for a sample, right, we can think about our data in terms of our raw outcome, y. We can split it up into what we call a deterministic or fitted part and an error part. The error part is simply the residuals, or the deterministic part is simply, or fitted part is simply a function of the y hats. Right? All we're doing is we're saying for every single person or every single observation in our data set, each of those rows, that outcome can be viewed as a function of our fitted y hats, all right, the predicted y hats, and that part which is not predicted by our line, the error or residual. For population, we use a slightly different notation, but the same idea holds. You have a fitted component and a stochastic or error component. Now we can think of this outcome in terms of a line plus a residual term in which these errors or residuals tell us how far off each person's outcome value is from the line for a given value of x. Right? Now, how do we estimate, how do we derive these values for the intercept and slope? Because we can fit lots of lines to any single scatter plot of data. Well, we use the method of least squares. It's by far the most commonly used algorithm for fitting a line to a scatter plot of data. In fact, simple linear regression, without additional information provided, it's probably based on the method of least squares. Sometimes simple linear regression is called classical linear regression. Right? That means it's using the least squares algorithm. Sometimes it's called ordinary least squares. Right? Synonymous with simple linear regression. Least squares is the method by which we obtain the intercept and slope. Right? The least squares method, the idea behind it is that we're trying to find values for the intercept and slope. We're trying to find the coefficients such that the sum of the squared errors, or to put it another way, the sum of the squared residuals, is as small as possible. Intuitively, all that means is that you want the line to fit pretty close to the data. You don't want those residuals to be really large. Right? In sort of the totality, you want those errors, those residuals, to be pretty small for all the people. So here's an example in which you can kind of view how we can decompose the variation of our outcome. So here we have some value, okay? And you can hear that we have a y hat value. We have a particular value for the mean of y, and then we have a particular value for the y hat. So we have these three benchmarks. You have the raw value of y, you have the predicted value of y, which we call y hat, and then you have the overall mean of y. Right? And for a given value of x, right, for a particular person here, that particular person or row of the data set, right, that person's value of the outcome, you can split up in terms of that which is accounted for by our model and that which is not accounted for by our model. In totality, we can kind of summarize it as follows. We can talk about something called the total sum of squares. Right? What this is a measure of the overall variability in our outcome. It's simply the raw values of y minus the mean of y. The mean of y is the overall benchmark for the variability in our data. And then we square this difference, this distance, for every single row of the data set, every single person in our data set, and we add them up. Right? Literally, it is the total sum of squares. Right? Statistics can be pretty straightforward sometimes, where the total sum of squares is indeed the total sum of squares. Then what we do is we can divide this in terms of that variation in the outcome, which is accounted for by our model, which we call the model sum of squares, and then that amount of variation in the outcome which is not accounted for by our model. We call it the sum of the squared errors. The model sum of squares is simply the y hats for all the people or all the rows in our data set, and then we subtract the mean of y, and we square it so that the values don't cancel each other out. We add it up together. And then for the sum of squared errors, we take the raw value of y, we subtract out the fitted value of y, the y hat, right, that distance, we square it for each person, for each row of the data set. And we can say that the total sum of squares is simply the model sum of squares plus the sum of the squared errors. Based on this decomposition, this decomposing of the variation in the outcome, we can calculate this measure of fit, which we call R squared, sometimes known as the coefficient of determination. R squared is simply the model sum of squares divided by the total sum of squares. Well, total sum of squares is simply the raw values of y minus the mean of y squared for each person, for each row of the data set. The model sum of squares consists of the y hat for each observation minus the mean of y squared. So when we do the ratio of the model sum of squares divided by the total sum of squares, we have the proportion of variation in the outcome accounted for, explained by our regression model, by our input variable, x. We can also calculate R squared by taking 1 minus the sum of squared errors divided by the total sum of squares. That's because the sum of squared errors divided by the total sum of squares, that's the proportion of the variation in our model, in our outcome that is not accounted for by a model. So the sum of squared errors divided by the total sum of squares is the total amount of variation not accounted by our regression model. So R squared, it's a proportion. It lies between 0 and 1. In general, a higher R squared and R squared closer to 1 suggests a greater proportion of the variation in the outcome is accounted for, explained by our regression model. Another measure of model fit is something we call the root mean square error. Root mean square error is simply the square root of the mean squared error. Sometimes called the mean squared deviation or the root mean squared deviation. Sometimes it's called the residual standard error. The basic idea is the same. What we do is we take the sum of the squared errors, we divide by the effective degrees of freedom, and we take the square root of that. What this is doing is it's giving us an idea of the size of the average residual, the size of the average error, with the idea being that if we want to use our model for prediction, on average we want that residual to be pretty small. We want that error to be pretty small. A larger residual suggests our model's not going to do as good of a job for prediction than if we have a smaller root mean square error. So it's another measure of model fit. Often R squared and root mean square error will go together, but not always. Right? They are really different measures of model fit. One gives the proportion of variation in the outcome accounted for by our model, that's R squared. Another one gives us an idea about the size of the average residual, root mean square error. If you're really using a model for prediction, right, you're probably going to be more interested in the root mean square error because your goal is to make it so that the residuals are going to be pretty small. You don't want to use a model that predicts if the root mean square error is quite large. That suggests you'd expect your prediction to be off. So you want a relatively small root mean square error if you're having a model for prediction. And often people do use regression models for prediction. So if you look at your credit score, these credit agencies will use a regression model to predict your credit score or predict people's credit scores. They will use regression models to predict consumer behavior. They'll use a regression model to predict where people are going to shop. The point is that all these models are really focusing on the root mean square error. They want that root mean square error to be relatively small. And with that, we've really covered the basics of descriptive statistics. We've covered how to describe data, categorical numerical data using tables and graphs, and also summary statistics, such as the mean, proportions, and so on and so forth. We've also covered basic measures of association, such as relative risk for two binary categorical variables. We've also covered covariance and correlation. And then we've also covered simple linear regression, in which you fit a line to a scatter plot of data for the purpose of description or prediction. The next part of our lecture, we will talk about inferential statistics.